Hello and welcome to Math Zone African Motives. Today, we're diving into a fundamental concept in Electrotechnics N4, the factors that influence the resistance of a conductor. This is Unit 1.4, and by the end of this lesson, you will be able to state these factors, use the formula to calculate resistance, and apply your knowledge to solve complex circuit problems. So, what exactly affects how much a conductor resists the flow of electricity? There are four key factors. First, we have length, represented by the symbol L. Second is the cross-sectional area, A. Third is resistivity, represented by the Greek letter rho, R. And finally, there's temperature, T. Let's explore each of these in detail. Our first factor is length, L. The resistance of a conductor is directly proportional to its length. This means that if you double the length of a wire, you also double its resistance. Imagine a long, narrow road. It's harder to get from one end to the other than it is to cross a short, wide road. Length is represented by the symbol L and is measured in the SI unit of meters, or M. Next is the cross-sectional area, A. This is the area of the conductor when you slice it in half. The resistance of a conductor is inversely proportional to its cross-sectional area. What does inversely proportional mean? It means the opposite. A bigger cross-sectional area results in a smaller resistance. Think of a highway versus a single-lane road. The wide, multi-lane highway can handle more traffic, just as a thick wire can handle more current. Cross-sectional area is measured in square meters, M2. Since most conductors are cylindrical, like wires, we often need to calculate their cross-sectional area. The formula depends on whether you have the radius r or the diameter d. The first formula, A equals PR squared, uses the radius. The second formula, A equals pi d squared divided by 4, uses the diameter. Our third factor is resistivity, R. Resistivity is a property of the material itself. It tells us how much a specific material opposes current flow. The formal definition is that resistivity is the resistance between opposite faces of a 1-meter cube of that material. Think of it as a material's inherent difficulty for electrons. Some materials, like copper, have low resistivity, making them excellent conductors. Others, like rubber, have very high resistivity, making them good insulators. Because it's intrinsic to the material, resistivity is also known as specific resistance. It is represented by the symbol rho, R, and its SI unit is ohm meter, or ohm. The fourth factor is temperature, T. For most pure metals, including copper and aluminium, resistance increases with temperature. As the temperature rises, the atoms in the conductor vibrate more, which makes it harder for electrons to pass through. However, for the problems we'll be solving today, we will assume that the temperature remains constant. Now that we know the factors, how can we calculate the total resistance? We can combine length, area, and resistivity into a single formula. The formula for the resistance of a conductor is R equals rho times L divided by A. This is one of the most important equations in electrotechnics, so make sure you memorize it. Let's break down the units. Resistance R is in ohms. O, length L is in meters M, area A is in square meters M2, and resistivity R is in ohm meters, OM. Always ensure your values are in these SI units before you calculate. A common mistake students make is using the wrong units. Let's cover some essential conversions. First, for length. To convert from millimeters, M, to meters, M, you divide by a 1,000 or multiply by 10 to the power of minus 3. To convert from centimeters, ISM, to meters, you divide by 100 or multiply by 10 to the power of minus 2. To convert from kilometers, kini, to meters, you multiply by 1,000 or 10 to the power of 3. Now for area. To convert from square millimeters, mm squared, to square meters, m squared, you must multiply by 10 to the power of minus 6. For square centimeters, cm squared, to square meters, multiply by 10 to the power of minus 4. This is a critical step. A single millimeter error can lead to a calculation that is 1,000 times off. Always check and double-check your units. Similarly, we need to be careful with resistivity units. Resistivity is often given in micro-ohm meters or micro-ohm centimeters. The Greek letter mu, m, stands for micro, which means 10 to the power of minus 6. So if you have 0.017 micro-ohm meters, you multiply by 10 to the minus 6 to get 0.017 times 10 to the minus 6 ohm meters. If resistivity is given in micro-ohm centimeters, you have two conversions to do: micro to 10 to the minus 6, and centimeters to 10 to the minus 2. This gives a total conversion factor of 10 to the power of minus 8. For example, 1.72 micro-ohm centimeters becomes 1.72 times 10 to the minus 8 ohm meters. Now, let's put this into practice with our first worked example. Example 112. Calculate the diameter of a copper conductor with a resistance of 4.5 ohms and a length of 3.2 kilometers. We're given the resistivity of copper as 1.68 micro-ohm centimeters. First, let's write down what we're given and convert everything to SI units. Resistance R is 4.5 ohms. Length L is 3.2 kilometers, which is 3,200 meters. Resistivity E is 1.68 micro-ohm centimeters, which converts to 1.68 times 10 to the power of minus 8 ohm meters. Our main formula is R equals RL over A. We need to find the diameter, so we first need to find the area A. We can rearrange the formula for area A equals RL over R. Substitute our converted values into the formula. A equals 1.68 times 10 to the minus 8 times 3,200, all divided by 4.5. This gives an area of approximately 1.195 times 10 to the power of minus 5 square meters. Now we have the area. We use the formula for the area of a circle to find the diameter. A equals pi d squared over 4. Rearranging this for diameter d, we get d equals the square root of 4a over pi. Substitute our calculated area. D equals the square root of 4 times 1.195 times 10 to the minus 5, divided by pi. This gives us a diameter of approximately 3.901 times 10 to the minus 3 meters. Finally, we can express the diameter in millimeters. Since there are 1,000 millimeters in a meter, we multiply by 1,000 to get our final answer, 3.901 millimeters, and that's how you solve for diameter. Let's move on to a more complex problem involving a parallel circuit. Example 113. A 725-meter copper conductor is in parallel with an aluminum conductor of the same length. The total current is 200 amps, and 75 amps flows through the aluminum conductor. The copper conductor has a diameter of 6 millimeters. We need to find the copper resistance, the voltage drop, the aluminum resistance, and the aluminum diameter. First, we always list our givens, including the resistivities for copper and aluminum, and convert everything to SI units. Length is 725 meters. Total current is 200 amps, and the aluminum current is 75 amps. The copper diameter is 6 millimeters, which is 6 times 10 to the minus 3 meters. The resistivity of copper is 0.017 micro-ohm meters, which converts to 0.017 times 10 to the minus 6 ohm meters. And the resistivity of aluminium is 0.028 micro-ohm meters, converting to 0.028 times 10 to the minus 6 ohm meters. Part A asks for the resistance of the copper conductor, RCU. We'll use our resistance formula, R equals RL over A. We have the resistivity of copper, the length, but we need the cross-sectional area, AQ. The diameter is 6 millimeters, so the area is pi times 6 times 10 to the minus 3, squared, divided by 4. This calculates to approximately 2.827 times 10 to the power of minus 5 square meters. Now we have all the values for copper. RCU equals the copper resistivity times the length, divided by the copper area. That's 0.0197 times 10 to the minus 6 times 725, divided by 2.827 times 10 to the minus 5. The resistance of the copper conductor is 0.436 ohms. Part B requires the voltage drop across the combination. In a parallel circuit, the voltage across each branch is the same. So, the voltage across the copper conductor, VQ, will be the same as the voltage across the aluminum conductor, VAl, and this is our required voltage drop. We can calculate VQ using Ohm's law. V equals R. We know RCU is 0.436 ohms, but what is the current flowing through at IQ? We know the total current is 200 amps, and the current through the aluminum is 75 amps. The current through the copper branch must be the difference. 200 minus 75, which is 125 amps. So IOCU equals 200 minus 75, which is 125 amps. Now we can find the voltage. V equals 125 amps times 0.436 ohms. This gives us a voltage drop of 54.5 volts. For part C, we need to find the resistance of the aluminum conductor, RAL. We can use the same voltage, 54.5 volts, since the branches are in parallel. Using Ohm's law again, RL equals VAl divided by IL. That's 54.5 volts divided by the 75 amps given in the problem. The resistance of the aluminum conductor is 0.727 ohms. Finally, for part D, we must calculate the diameter of the aluminum conductor, DAl. We have the resistance of aluminum, RAl, which we just found. We also have its length, L, and its resistivity, RL. We can rearrange the main formula to solve for the area of aluminium, Al. Al equals the resistivity of aluminium times the length, divided by the resistance of aluminium. That's 0.028 times 10 to the minus 6 times 725 divided by 0.727 ohms. This gives us an area of approximately 2.792 times 10 to the minus 5 square meters. We repeat the process from example 1.12 to find the diameter from the area. The diameter of aluminium, DEEL, is the square root of 4 times its area divided by pi. Plugging in our values, we get a diameter of approximately 5.962 times 10 to the minus 3 meters, or 5.962 millimeters. We've covered a lot today. Let's recap what you've learned. You can now state the 4 factors that influence resistance: length, cross-sectional area, resistivity, and temperature. You can explain how each factor affects resistance and identify their correct SI units. Most importantly, you can use the fundamental resistance formula, R equals RHL over A, to calculate the resistance of a conductor or to find any of its other properties. This formula and the understanding of these factors are the bedrock for solving a vast range of problems in Electrotechnics N4. Practice these steps, and especially the unit conversions, as they are key to success. Here are some exercises for you to try on your own. Remember to pause the video and work through them carefully. Activity 1.4 has several questions to test your understanding. Question 1 asks you to state the 4 factors we discussed. Question 2 asks for the SI units of each quantity in the formula R equals RHOL over A. Question 3 is all about conversions. Question 4 has you calculating a diameter. Question 5 is a definition, and question 6 asks for an alternative name for resistivity. The final 2 questions, 7 and 8, are longer calculation problems, similar to the examples we just worked through. Mastering these will build a strong foundation for your studies. Thank you for joining us today at Math Zone African Motives. If you found this tutorial helpful, please subscribe to our channel for more Electrotechnics N4 lessons. Your support helps us create more content to help you succeed. See you next time. Don't forget to like this video and subscribe to Math Zone African Motives for more tutorials.